Hello everyone, welcome back to Bytes of CAC. So this is the fourth lecture of the process scheduling algorithm series, and we will be learning round robin scheduling in this lecture. Now round robin scheduling is purely primitive in nature, where each process executes for a certain time in the processor, and then it is the context of the process is saved and the process is primitive from the processor, and the next process is assigned to it. So they actually execute turn by turn. See, for example, that time limit for which a particular process executes in the processor be 4 time units. It is generally known as quantum in this language, in this operating system language. So there are 4 processes in the queue, as you can see in this screen: A, B, C, and D. So say we have dispatched A into the processor and we start a timer, and after the timer has completed 4 time quanta, there is a timeout and A is moved back to the queue. Now B will execute. After B is done, B will be shifted back after A, then C, then D, and finally again A will execute, since A has by that time moved to the head of the queue. So now let's see how it works. Let's plot the Gantt chart. So A is the first process in the queue, so we will start with A. So A starts from time point 0, executes till time point 4. We are considering that there are 4 time units of execution time for each process. So at time point 4, B is dispatched to the processor. So B executes from time point 4 to time point 8, that is 4 plus 4, that is 8. And then C is dispatched to the processor. C executes from time point 8 to time point 8 plus 4, that is 12. And next D will be dispatched to the processor, where D will be executing from time point 12 to time point 12 plus 2 in this case, because the burst time of D is 2. So as a result, it will execute till time point 14, and at time point 14, D is still left with 2 units of execution which it will not be needing. So what the operating system does is, operating system immediately allocates the next process. So in this point, that is at time point 14, again A will be allotted, since after D has completed, the next process to execute will be A, if we consider this as a circle. Now at time point 14, basically first round of the round robin scheduling completes. Now A is left with a burst time of 6 time units, B with 5 minus 4, that is 1 time unit, C with 12 minus 4, that is 8 time units, and D has completed the execution totally. So at time point 14 to time point 18, now A executes from time point 18 to time point 19. Since B is left with just 1 time quantum, B will be executing at time point 19. C will be introduced. So C executes from 19 to 23. Now D is finished and B is finished, and 1 round is completed. Now at the end of this round, A is left with 6 minus 4, that is 2 time units of execution. B is done, and C is left with 8 minus 4, that is 4 time units of execution. So at 23, A, it's again A's turn. So A will be executing from 23 to 25, and at time point 25, B will be executing from 25 to 29, and the entire process completes. Now we need to find out the wait time of A. Now the waiting time of A, now A has executed in 3 spells. Now this blue bar stands for A. So A has waited from time point 4 to time point 14. That is the in-between time of the first and the second blue bar. Next, from time point 18 to time point 23. So this plus this will be the total waiting time of A. That is 14 minus 4 plus 23 minus 18, that becomes 15. Now let's consider B. So the black bar belongs to B. So B has 2 rounds of execution. So B first waited from time point 0 to time point 4, and next B waited from time point 8 to time point 18. So 4 minus 0 plus 18 minus 8, that is equals to 14 is the waiting time of B. Now C has also executed for 3 rounds. The yellow bar belongs to C. So C has waited from 0 to 8, again from 12 to 19, and from 23 to 25. So 8 minus 0 plus 19 minus 12 plus 25 minus 23, that is equals to 17. And finally D had only one round of execution, and it was assigned to the processor at time point 12. So the wait time of D is from this point 0 to point 12, that is 12. Now let's learn a new formula. Like, so far we have known that the turnaround time of a process is equals to the finish time minus the arrival time. Now turnaround time of a process is also equals to wait time plus burst time. So especially I have used this one because in complicated charts like this, you don't really have to find out, okay, where did actually A finish, where did A start. So you don't have to remember so many things. You just find out the wait time and add the burst time to that, and you will be getting the turnaround time for each process. So for A, it's 15 plus 10, that is equals to 25. For B, it's 14 plus 5, that is equals to 19. For C, it's 17 plus 12, that is equals to 27. And for D, it's 12 plus 2, that is equals to 14. And your average wait time will be summation of these 4, that is 15 plus 4 plus 17 plus 12 divided by 4, that is equals to 14.5. And the average turnaround time will be 25 plus 19 plus 17 plus 14, that is equals to 85 divided by 4, that is equals to 21.25. Now let us make a comparison between round robin scheduling and first come first served scheduling. Now there is no point considering shortest of first, because first of all this is a primitive scheduling and that's a non-primitive one, and moreover we know that shortest of first always fares better. So now we consider the same processes with the same burst time, and arrival time for each will be considered as 0, that is all the processes were did arrive at the same time. Now if we make a comparison, we plot the waiting time of round robin, and this is the chart for the Gantt chart for first come first served algorithm, and based on that we have the wait time of the individual processes to be this. Now if you consider the average wait time, the average wait time in this case of first come first served is better. But if you consider the individual waiting time, say for a smaller process like D had only 2 time units of execution. It had to wait for 27 time units to actually get to the processor, whereas in this case the waiting time of D is quite decent. So for processes which have a burst time which is less than or equal to the time quanta that is allotted, definitely round robin fares better than, in many cases fares better than first come first served scheduling algorithm. Now you cannot right away say that this is better or this is worse. It depends upon the scenario. It depends upon how which were the processes which were submitted to the queue, and which had the processor time. There are so many factors to be taken in, but in general for a random process, generally a very short process will have a shorter burst time, generally will have a shorter burst time than first come first served scheduling algorithm. Okay, so I've gone through the past questions on round robin scheduling in different competitive exams, and mostly they've asked for the average turnaround time or to find out the average waiting time. And I've gone through and I've just found two questions which is a bit different from what is generally asked. So this was asked in GATE 2000 IT, where it said that if the time slice used in round robin scheduling is more than the maximum time required to execute any process, then the policy will, these are the four options: degenerate to SJF or shortest of first, degenerate to priority scheduling, degenerate to first come first served, or none of the above. Now, as we have seen in the round robin scheduling, that the processes are dispatched to the processor in the order in which they appear. Say A, B, C, D, as we have seen. So A was the first process, so A was dispatched to the processor first for some time quanta, then B, then C, then D. So in case, since it said that the time quanta or the time slice was more than the maximum time required to execute any process, so say the time quanta was q, so at q time quanta A, B, C, D, all the processes finished their execution. So that is equivalent to the first come first served scheduling. So C will be the right answer to this. Next, I also came across a question like this. It appeared in GIT CAC 1996 and in EASRO in 2008. So it says that there are n processes sharing the CPU in a round robin fashion. Assume that each process switch takes s seconds, and what must be the time quantum size q such that the overhead resulting from the process switching is minimized. At the same time, each process is guaranteed to get its turn at the CPU at least every t seconds. Now there are processes from say P1 to say Pn. So let us consider that P1 has finished its execution. So P1 will have a switching time of S, and then P2 will be dispatched to the processor. Now since again after P2 is done, P2 will have another S amount of switching time. So there are n processes. So number of time, that is a switching time, needed in this case will be n into S. Now let us see what is the minimum waiting time of P1. Now after P1, P2 to Pn will be processed, and after that P1 will start executing in the round 2. So essentially n minus 1 processes will be executing after P1. So the waiting time of P1 in each round will be equals to n minus 1 into the time slice that is given, that is q. Now the total waiting time of each process will thus be ns plus n minus 1 into q. Now that should be less than equals to t, because it says that it should be guaranteed to get a turn at the CPU at least every t seconds. So this summation should be less than equals to t. Therefore q should be less than equals to t minus ns divided by n minus 1. So A is your answer. So that was all about round robin scheduling. If you come across questions, difficult questions or different questions which you are finding it difficult to answer, you please let me know in the comment box. And if you have liked my video, please give me a thumbs up, and there is a link in the description box that takes you to a MCQ site that contains some questions regarding process scheduling, and I highly recommend you to go through those questions and find out how far you have learned. So thanks for watching. That's all for today.